Hello, I'm Randy Roebuck. I lead the technical activities at OmniAir. Today we're going to be covering LTE V2X technology, introduction to the tolling agencies. We want to come here today to explain the power of V2X. It's both direct and network. It does many things for you. It sees around the corners. It gives information for both safety and mobility, consisting of uh, transit vehicles, regular vehicles, public safety vehicles, and the communications that can help us all in promoting safety and having a safer environment. OmniAir itself is, we do trusted VDEX communications in the transportation sector. We were founded in 2004. We deal with conformance and interoperability for the transportation technologies. We have a very diverse membership of 90 plus members, and we deal with the device suppliers, laboratories, test equipment, engineering firms, research institutes. Uh, we have two basically sectors in OmniAir. One, the connected vehicle. The second is the traditional RFID tolling. Now they're starting to merge together, bringing this new communication technology to the tolling sector. In the past, on V2X, we went from DSRC to V2X, and V2X now has two flavorings, direct and network. Uh, Whereas RFID tolling, it operated with single and multi-protocol readers to read, but I'll explain that later in the slides. And it also has a safety security component. Certification builds trust. On the left-hand side, you can see all the elements that we check for in devices to make sure they're compliant to the standards and the requirements as needed to provide a um, conforming device, having interoperability, and provides reliable service. Certification covers the entire communications protocol elements. It goes way beyond the radio PHY. It does provide assurances to the stakeholders that the system or the technology has been vetted. It provides an avenue for technology to provide validity, and along with standardization, certification promotes conformance, interoperability across the transportation technologies and jurisdictions. On the right-hand side, you can see the result of our certification. These show the first devices in each sector that got certified. We had IT Telecom out of Korea certified to the US standards, and it's the same standards they use in Korea. In the tolling world, we have the CAPS Trafficom reader that just got certified actually for all three protocols in the UHF RFID space. Communication device certification from the US DOT. These are their slides, what they determine as interoperability and interoperable connectivity. It's standards-based. It takes industry cooperation to come to this point. Um, the vehicle from the OEM needs to communicate with others. So regardless of where they're at, all devices need to transmit and be able to be received in order to provide the critical safety messages. In the interoperability connectivity, they basically described it as a diverse range of mobile, in-vehicle, and roadside devices that communicate efficiently and securely in a privacy-protected manner using multiple wireless communications technologies, wireless messages, and open data formats and standards. At OmniAir, you can go to our website and In our website, it shows the OmniAir certification. You can go to the page that's listed there with the QR code. There's two documents that we have open to the public that describes our certification scope, matrices, all the components in it. Also lists all the LTE available test case listings in these documents. In the middle, it has the certification scope and the different elements that make up our RSU certification release one process. And right beside it, you can see all the devices that have been recently been certified to the RSU certification scope. On the right-hand side, it's the OU release one scope, and you can see the devices that have passed there, all the way from Edifice, IT Telecom, Unix, and in our RSUs, we had Coda, Casigna, IT Telecom, and Unix. This scribe kind of describes all of the V2X communications. Uh, It shows the V2X and the ITS road infrastructure, which includes a traffic signal controller and the RSU, the V2X communications to the vehicle, where there's a CAN bus interface, or there's basically just the radio broadcasting and getting the messages. And then its data actually showed on an HMI screen for the applications. On the right-hand side, you got the back office. And typically these back offices are local or regional. It's not national. And it gets all the information and provides all the data and the histogram and that. Uh, Down below, part of the system is the position and timing, or some people may know it as GNSS or GPS. You can see device certification, and you can see the security credential management. In the center, uh, the messages that go cross over the air are the basic safety message, the SPAT, the map, the single request, the single status, the emergency vehicle alert, the traveler information message, the roadside message, and the personal safety message. We will get into more details on those type of messages. What's the difference between UHF, RFID, and VDEX technology in the vehicle transportation space? Over-the-air communications, the RFID is a one-way localized. It's about 10-meter distance that reads. In VDEX tolling, it's a two-way, semi-localized, about 300 meters. The RFI protocols used in tolling are the TDM, the 6B80K, and the ISO 6C. And VDEX tolling, they use the 3GPP, PC5, R14, which is called the direct, or the UU cellular network. Environmental conditions, communications. There really isn't anything from the tolling outside of going from the gantry to the car, but there's no interface. However, the VDEX tolling, the OBU, can be connected to the vehicle through the CAN bus or the USB Automotive 3 device, or the infrastructure as far as a traffic signal controller. This kind of calls talking cars. Or which they call V to I. FCC, it's very similar. The reader or the RSU are both Part 90. The tag in tolling, the passive tag doesn't have any regulatory requirements, whereas in the VDEX tolling, its OBU electronics device is deemed as Part 95. VDEX tolling is a very standard space. All the standards we'll be going through today. The architect tooling, there's some basic standards from the AIR protocol, uh, but the VX tooling is more or less a pure standards-based communication technology. Line of sight, Uh, Tolling does not do non-line of sight, and V2X can see around the corners. The tolling basically gives a very ID coming from it, very small data, very small. It is low latency from the short distance, and the V2X tolling actually has a high data that can be put into it, but manageable and a very low latency. Location determination. The tolling is constructed where the antennas are very points down, going through the gantry, very small read range, where it picks up the car going through it. Whereas VDEX tolling is based on GPS, so you always know where the vehicle is from a location standpoint, and it gives you about a 1.5 meter radius as a requirement, but many vehicles are doing much better than in open sky. And if you add RTCM to it, you can actually get down to plus or minus zero point 0.1. So it can easily do the lane level type accuracy that's needed for tolling. Security, authentication is limited, whereas the V2X has been designed with security certificates for authentication. It has a hardware security module per the FIPS 140. It's very has privacy and enmity built into it, and it also has a misbehavior returning mechanism uh, order to if there's no go any bad actors. Far as applications, the tolling is very lane level and it deals with parking and tolling. And VX tolling has a vast amount of lane level and road level applications that can be used. As far as the technology status, RFID tolling is very mature and very low cost. The VX tolling electronics is emerging in the vehicles and infrastructure now. This screen shows V to X or connected vehicle. You can see on the right-hand side the example of information messages. You have the V to V, which is the vehicle to vehicle, and the key message there is the basic safety message that gives you a the information from the car for its position, speed, brake status, acceleration. Then you have V to P, which is a personal safety message. And you have the V to I, which is the vehicle to the infrastructure, such as a traffic signal controller showing the light status, the map, and the signal request message. Then you have the traveler information message, which is also a V to I. It basically allows you to have the transit signal priority, the emergency vehicle preemption, the freight signal priority, and other advanced signal operations and speed harmonization and betooling that comes from those messages. You can see below the technologies in today's vehicles where you have forward collision warning, lane departure, blind spot warning, emergency braking, pedestrian emergency braking, and adaptive cruise control. VDAX and adding communication to this even brings a more reliable system versus these line of sight sensors. And up the top at the upper left, you can see the dashboard of the car, and you can see the bicycle warning. You can see in the middle where you're going down the lane and you have something turned into it. And at the bottom, you can see it's using direct C to V to X. So automobile makers are starting to integrate it into cars now. The LTE technology basically uses the direct V to X, which is the LTE V to X PC5, and also the network V to X, which they call which they use the UU cellular portion as a standards-based two-way communication used in lane level and road level safety applications. There's security encrypted in their standards of 6009.2 incorporates authentication slash trust, anonymity and privacy. By doing that, they use a pseudonym or identity application search, depending on what type of unit it is, coming from a security credential management system. And actually, they have a mechanism where the vehicles and the RSUs in the field can be updated per the 609.2.1 and the 609.2.2 standard. As an OBU, the standard that they follow is the SAE J5001. There's also a standard for aftermarket devices, which is the J3315, and they use a radio protocol J3161/1. Gives you about 300-meter read distance as geofencing. And of course, it has the GPS precision accuracy, where it broadcasts messages at 10 hertz. This 10 hertz came along where if you're moving 70 miles an hour, it basically equals about 10 feet per BSM, or about 0.67 of the vehicle length. So you always know where the vehicle is based on the BSM broadcasting every 100 milliseconds. OBU types, there's embedded, and there's the aftermarket, and they have three different categories of aftermarkets: ultralight, light, and pro installed. There's standards both for passenger light vehicles, which is the J3161/1, and the public safety vehicles is put into the version 2022, and the motorcycles follow the J2945/1B, and school buses 1C, which basically gives unique parameters beyond the passenger of the J3161 protocol. And there's basically one OBU per vehicle. The RSU, it follows the CTI 4001 standard and has field implementation, such as connected intersections, which follows the J4501 and the 4502. It has about 300-meter read distance and beyond. It broadcasts SPAT map, TIMs, SDMs, SSMs, and RTMs. And the vehicle applications do EEBL, which is electronic brake warning. RTA is right turn assist. Then we have SCSW, which is curve speed warning. And then the tolling applications, they follow the J3217 for the open road overhead gantry, and the road using charging, which is the J3217R. The V2X use cases and vehicle infrastructure, you can see at the top, they have high precision. We do device certification on it, make sure the devices are working properly and been checked out. And there's a security management system. And here, this particular chart kind of shows what applications need what type of latency. You can see on the left-hand side, crash imminent, where it needs a response of less than a half a second. Then you have crash warning messages that are usually less than 5 seconds, such as a curve speed warning. Then you'll have alerts and advisories, which is less than 60 seconds, which an example of that is work zone. And then you also have information/support, which is greater than 60 cents, which is like traffic monitoring and surveillance. There's a whole bunch of standards that make up an LTE-V2X device. And it goes all the way from the radio filer from 3GPP down to the IEEE 6009 standards, which cover security certificates, security interface, and network services. The PSID identifiers and the V2X message structure. Then you get into the J3161, that is the OBU modules. Then you can get down to the Insight, um, which is the messages from the infrastructure agency uh, through the traffic signal controller and the RSU. And then you have the ITE 4001, which basically is a unique standards for the RSUs. OmniAir itself, we provide certification services. Basically, our group looks at the standards, the requirements, and the regulatory. We have 90 plus members uh, that participate in a variety of working groups. These working groups looked at these requirements. They develop the test cases and scopes, and which leads to the validation. Um, we have a qualified test equipment, which we go in and make sure the test equipment meets the standards, providing the correct evaluation of what's testing. We have authorized test laboratories, so we put them through an audit to make sure they know how to use the test equipment, the test cases, and actually test a device to produce a test report. We also have authorized field test sites that's done outside of the bench testing, and which leads all to device certification. One of the important things in V2X is test tools. Uh, we basically go in and audit and qualify the test tools, make sure they're reading what they're supposed to, giving a proper representation. Very helpful out there when you're developing devices and verifying them, and also for agencies who are implementing that can see what's happening out there and make sure that uh, the proper functionality is working in their implementations in the field. You can see there's an iTerra's tablet. You can see a CAPTCH test tool there in the center top. Then on the right top, the Keysight WaveBee. Then on the bottom left, the SAENI um, sniffer. We also have the V2X hub that generates messages and feedback to make sure it's doing it properly. Then you have the Waities sniffers with Wireshark to decode the messages. Um, One of the important parts of interoperability and conformance is the message set dictionary. There's the SAE 2735. The latest version is 2024. It has a modularized ASN1. You can see on the right-hand side all the message types and many different um, elements make up these messages that are below. It reads all the way from the basic safety message down to the traveler information message and test messages that are available that's implemented into the device. Another important component in the system is the roadside unit, which we call the RSU. You can go to the ITE website to get the CTI 4001. The last public version is 2021, uh, and it makes sure it can transmit the messages properly and also receive the messages from the vehicles. Some of the main messages is signing and forwarding messages, forwarding the messages that are already signed. They do a store and repeat a message broadcast, such as a map message, and then they also forward messages back to the network. The vehicle on board unit, which we call the OBU, There's a standard that's in works right now called J5001. There's also the PSIDs, that is your J3268, and there's also the aftermarket devices, which you can see on the lower left-hand corner in this table where it shows a summary of the AVD categories, and you can see there's three different types of AVDs. There's the ultralight, the light AVD, and the Pro AVD. And basically, depending on the characteristics of that device, is what they're qualified for and actually get certification and security certificates to be able to do certain operations based on their hardware capability. These devices all use the LTE-V2X protocol, which is J3161. If it's /0, it's the RSU, /1 is the OBU. There's two different radio configs out there. That's why you see two different standard versions of the standard, which is 2022 is basically without SLSS radio config, and the 2024 version is with it, with the allocation so we can have interoperability. All devices have to operate with this same radio configuration in order to be fully interoperable. If you're looking for the BSM procedures, this J3161 actually calls out the parameters in J2945/1 2020. You can see the documents table of contents and the makeup of the particular protocol. You can see the pictorial in figure 1 here makes up an OBU where you have the GNS antenna, the receiver, you have the OBU processor, you have the PC radio config, then you have the safety applications. And then you also at the bottom have the security credentials. In the very bottom here, which is table 15, this shows the parameters for the different configurations of a AV from going from DSRC to LTE. Here's a test tool. This is a Linux tablet. It's basically capturing messages where it's connected to a radio proxy OBU. This one is displaying both BSM, SPAT, MAP, and TIM and WSA messages. You can see here this particular, I have multiple OBUs in the same vehicle, kind of showing how they track with each other. They also are showing the SPAT timing that's coming across. They also have the other OBUs that they see in the car here. If you click on one of their other screens, you can actually see the messages. The one with the down arrows is what's being received, and this particular tool where it shows going up is what's being transmitted out of the test tool, so it can show its position and field. If you click on one of these messages, you can see the WSA is click. You can actually have the message and the headers in that perspective. This actually can receive it. You can actually do a playback in the recordings to track how you're going through the intersections. You can save the messages and analyze them later. This is the content of a signed BSM. And you can see at the top where we're capturing, you can see the basic safety messages. There's 10 of them coming through at a time from each OBU. If you see here on the signer, that's a certificate packet. The one is a digest. It's a smaller packet. It's already been vetted. Certificate packets are sent every half a second from each vehicle. You also have a map message. You also have a SPAT awareness message here. And you can see the contents here in the BSM Part 1, which all these elements are mandatory to be there, and depending on the conditions, whether they're populated or not, you got a message count, the temp ID. When you're under security, that will change at 5 minutes and 2 kilometer requirement order to protect your privacy and anonymity. Uh, it does give you the GPS accuracy, which I don't have uh, exposed. Then you can see the speed, the heading, the vehicle size. Then on the part 2 data, that shows the characteristics of path history, path prediction, radius of curvature. And here is an excerpt of what a signed message, and this one basically is showing the digest and hash and the public key signature. And there's usually 8 digests per second, and the other 2 are certificates. And you can see on the right-hand side what makes up the certificate, what permissions it gives it, and that. This particular slide shows how accurate and how tracking will or the precision going through the lanes. So we basically was going through an intersection, different routes through there, testing its precision. In the car, I had 4 OBUs in the same vehicle, kind of wanted to see how consistent representative they are with each other. This is really blown up at a very high level. Uh, this accuracy of these devices are in the plus or minus about 2 meters. So it gives very good lane level accuracy. Here in the center, lower, we are testing to make sure that its path prediction and its radius of curvature are tracking. And here you can see with a test tool, and we had cones marked out. You can see how consistent the BSM is going around this circle. One of the things is you want to make sure the devices is accurate. So we actually have a test tool that has ground truth GNS in it. It has an accuracy of plus or minus 4 centimeters in open sky. And it basically compares the OBU that's in the car as the device under test and compare their values with the ground truth test system. And it shows how accurate it can get. This particular chart here is showing 3 different OBUs. You can see the top is very, very good, meeting the requirements very well. You can see the second one is not meeting the requirements and needs some more work done. And the bottom one, it shows an OBU in a car that's showing pretty good accuracy, but they did not apply the offsets to make sure this was in the center of the vehicle. So this one's very easily correctable, and it would look like the top one if they applied the offsets. One thing we want to make sure that in security, it's changing its certificates according to the document. And in our certification testing, we want a minimum of 4 certificate changes, and this is about a 30-minute drive. So the criteria is it must change at 2 kilometers and plus 5 minutes to meet that criteria. So we do a little bit of rural road, a little bit of interstate to make those representations. And we want to make sure that this functionality is followed. on the far right-hand side, you can see the heading latch and unlatch. They want to make sure that, hey, once it's going so slow that it latches its parameter as the last known good spot. And then when it gets above the speed, it will unlatch again. The bottom here for hard braking, uh, um, basically, we want to make sure that it triggers this point and will actually give a alert message to the car following behind you. So a car actually, if you're coming up to a stop sign and you hit the brakes and because you really didn't allow much time to do that, you'll trigger that you're coming to a sudden stop. And then here you can see in path prediction, you see one OBU is doing it very well. Then you can see on the right side here, another OBU actually wasn't tracking as well as it should. And then the device manufacturer goes back and corrects that. Here shows an example coming off of the um, test tool, and this is a Wireshark capture where we're showing the different messages. You can see the gray line up above saying that it's an SRM, it's a wave service announcement. So basically on the lower left-hand corner, you can see the WSA, the wave service advertisement, and it actually has an SRM service uh, requests at this intersection, and that's what's shown below. In the middle, we have a map message that gets decoded. Here's the major elements. Then when you click on those items, you can get a lot more detail that comes from the map message. And the single phase and timing, this shows the breakdown of a SPAT, shows the intersection ID. It shows different elements and what single group, and each one of these items has basically what the status of the traffic signal controller is. How do we apply this to tolling? So there's a standard that was created called J3217, V2X tolling. It takes all this basic V2X functionality from the OBUs and the RSUs. You can apply an RSU at a tolling gantry. Basically, one could serve all the lanes, whereas now in tolling, they have to have a reader in each lane. And they can basically pick up all the vehicles going through, and with the GPS in each vehicle, it knows exactly how it's positioned and where it's going through. Um, so it can very effectively do it. The uh, roadside unit does require RTCM, which is basically a GPS correction. So there's sometimes where our issue is put where it doesn't have good open air sky or between very tall buildings, and you can actually get a correction factor brought down to the RSU where it can broadcast to the OBUs and actually give the OBUs higher precision. So this offers onboard support for onboard units, which we assume the tolling agencies would use existing OBUs out there, apply it, and the tolling app can be applied to this technology. And if it's not embedded or built into your car, there's aftermarket safety devices that can be applied. The new message types that was developed for tolling, you have the WSA that has the announcement in there. Then you also have a traveler's advertisement message. You also have a TUM, which is a traveler user message, and it actually gets encrypted going back from the vehicle to the gantry. Then you have a TUM acknowledgement. The next slide shows how the tolling works going from the OBU to the RSU to the toll service provider to the toll charger. Basically, the vehicle is the OBE. The roadside unit is at the overhead gantry. Um, in the infrastructure, it basically has a communication change two-way going back and forth. So if the OBU comes to the gantry, it sees that there's a toll advertisement message. So so with the TAM, then they actually can then broadcast a toll usage message, which has the information of the vehicle, the payer, and the fee, and it responds back to the gantry structure as a TUM, and it is encrypted. And then once a gantry sees it, it goes back to the network. It says, hey, this is good. Then it'll give a message back to the RSU to send back a TAM acknowledgement that, hey, it was charged, it was verified the signature, and so it was received, and it will go up to the network and basically say, hey, payment can be applied. Since this is time critical at that stuff, it doesn't necessarily mean that it ended up being a successful payment. The other part of tolling is road user charging. Um, so the J3217R has been developed where it can apply this road user charging mechanism to the V2X, take advantage of that. It was really designed for cellular, smartphones, network V2X, because you may not have an overhead gantry everywhere, or and this particular standard is communication protocol independent. It does offer a very enhanced user privacy with robust security and a certificate matching section. And it was designed to ensure that there's no tracking of end users. So it was actually really designed and built for the technology and to give a payment service there. Thank you very much for this seminar, V2X in the tolling world. And this is my contact information if you want to reach me to ask about OmniAir and the technical aspects of V2X. Thank you very much.